Yes.
Okay, great. So yeah, let me start by thanking the organizers for the opportunity to present my work. It's actually the first time that I'm attending this conference, and I must say that I really enjoyed it. I enjoyed a lot of talks for the past 3 days. So thank you for having me here. My name is Beata Zjawin, and I'm a PhD student at the International Center for Theory of Quantum Technologies at the University of Gdańsk in Poland. And we have a Quantum Foundations group here. The leader of the group is Anna Belen-Sainz, and as you can see, she's also a collaborator on this work, as well as David Schmidt and Matti Homan. So today I will talk about quantifying EPR, the resource theory of non-classicality of common cause assemblages. We recently put this draft on our archive. So if you find what I will be talking about interesting, you can of course ask me questions, but I also encourage you to look at the paper. Okay, so let me start with a question. Is quantum steering spooky action at a distance? Because it is sometimes called this way. So the steering phenomena is a form of non-classical correlations that arise when one considers measurements performed on half of a bipartite system prepared on an entangled state. So if we try to represent the situation graphically, we end up with a picture like this. Here, the double lines correspond to quantum systems and single lines correspond to classical systems. So we have two parties, we have Alice and we have Bob, and they share an entangled state. Alice prepares measurement on it. So this represents a measurement device that takes a classical input X and outputs a classical variable A. And now, depending on X and A on Alice's side, Bob's system can be described by this conditional quantum state, rho A given X. So why is it sometimes called a spooky action at a distance? Well, it is because Alice and Bob are two space-like separated parties, but it seems that Alice can somehow steer Bob's system into this conditional state. So the term steering was actually given by Schrödinger himself, and he called it that because from this scenario, it kind of seems that maybe Alice has an influence on what's happening in Bob's laboratory. But this is not the only perspective that we can take when we talk about this scenario. And a different one was endorsed actually by EPR themselves, so by Einstein, Podolsky, and Rosen in their original work. And it is that simply Alice updates her knowledge of the state of Bob's system by performing a measurement on a system correlated with his. And of course, it makes perfect sense that Alice and Bob share a correlated system. So when Alice learns something about it, she also updates her knowledge on what's happening in Bob's laboratory. So is steering spooky action at a distance? Well, not really. It's neither spooky or action at a distance. And because of this, throughout this presentation, I will not refer to this phenomenon as steering, but simply as EPR scenario, where again, EPR stands for Einstein, Podolsky, and Rosen. So well, we could say that it's just a change of name, and maybe from a technical perspective, well, it doesn't make much difference. But from the foundational perspective, it actually makes a huge difference how we look at this scenario. So let me just recap everything that I just said. So from Schrödinger point of view, he called this phenomenon quantum steering uh, in a sense that quantum, because he thought that quantum state is a physical property of a system. And then the fact that Alice steers Bob means that there is some kind of superluminar causal influence. So in the modern language, we would call such beliefs a psi-ontic view, which basically means that distinct quantum states describe distinct physical states of the world. While what EPR interpreted it as, they said, well, spooky action at a distance is not really acceptable. So quantum state, we can take it to be a representation of one's information about the system. And then in this scenario, Alice simply learns about the true state of Bob's system. And this point of view could be described in a modern language as a epistemic, sorry, which is basically that quantum states represent states of knowledge about the world. Okay, so after this foundational motivation, let me go into the actual resource theory. Okay, so we will talk about EPR scenarios, and what we take to be the defining features of an EPR scenario are the following. First, common cause causal structure. So as I said, we have two parties, Alice and Bob, and they share a common cause, which in this case is quantum. And the second defining feature of this scenario are types of systems that parties have access to. So on Alice's side, it will be a classical input and a classical output, while on Bob's side, it will be a trivial input because he has no input at all, and a quantum output. And it's very usual to describe EPR scenarios with quantum assemblages. So a quantum assemblage is an object like this, where each conditional state contains information about what's going on Alice's side. So this probability distribution of obtaining an outcome A given an input X, and what's happening on Bob's laboratory, so this conditional state. Okay, so we want to create a resource theory of assemblages. Resource theories allow one to formally quantify physical resources. So in our case, the resources are assemblages, and what we want to quantify is their non-classicality. The structure of a resource theory is completely determined by the set of free operations. So free operations are operations that cannot create a resourceful object. And because of this, they can also be applied to different resources for free. Because if we apply a free operation to the resource, it will not increase the resourcefulness of it. And now for the case of assemblages, our approach follows the recent developments of resource theories for studying non-classicality of common cause processes, wherein the free operations are local operations and shared randomness. So as I said, an EPR scenario is simply a common cause process. And because of this, we take a lesson from some papers that were already published when common cause processes are studied with LOSR operations. And in particular, there's this paper here that basically creates a new branch of entanglement, LOSR entanglement, in contrast to LOCC entanglement, where CC stands for classical communication, and that people usually talk about. And in this paper, it is shown that taking this LOSR perspective actually resolves some anomalies of entanglement. And there is also this paper here, which treats common cause boxes, so things like Bell scenario, where we have a common cause structure again, but here both parties just have access to classical inputs and classical outputs. And because we can study both entanglement and Bell-type scenarios using LOSR, it means that we can also study their interplay, which is really amazing because it means that we can have like one unified resource theory of common cause processes with different types of resources like entanglement, Bell boxes, or assemblages, and we can study their relative non-classicality. I would also recommend this paper if you are interested in this stuff because it talks about a type-independent resource theory, which considers even more types than just entanglement, assemblages, and Bell boxes. So let's just say that in the literature, it was pretty well motivated to study LOSR for common cause processes. But even from simply looking at the EPR scenario, well, we can see that it is a common cause process. So we have two parties. It's perfectly fine to allow local operations for each of the parties. Local operations can be classical or quantum. There will be quantum on Bob's side. And because we want to study the non-classicality of assemblages, we do allow classical common causes for free. So what you can see on this picture here on the right is an assemblage where the common cause is classical. So Alice gets a classical variable lambda, and she performs her measurement, while Bob prepares a quantum state depending on the value of the classical variable. And we call such assemblage a free assemblage because it can be created solely by free operations, so LOSR operations, and it can be decomposed like this. So on Alice's side, we just have this probability distribution where lambda is the shared variable, and on Bob's side, he prepares this quantum state. So for now, I'll just mention that there are also different approaches to studying non-classicality of assemblages. And there is one resource theory that was developed a few years ago that the set of the free operations in this resource theory was stochastic one-way classical communication and local operations. And after I'll introduce our approach, the LOSR one, I will compare it to the previous one, but I'll do it later on in my presentation. Okay, so what are these LOSR operations? Here in black, we have the original assemblage, and now the most general LOSR operation that we can perform on it is first on Alice's side. We have a classical pre-processing of this classical variable. We have a classical post-processing of the output variable. On Bob's side, we have this post-processing of his quantum state. So this will be just a CPTP map. And now the actions of local operations on Alice's side and the local operation on Bob's side can be correlated by shared randomness. So classical common cause. So this would be the lambda that's distributed to Alice and to Bob. Okay, so now that we have a resource theory and we have the set of free operations, we can study the properties of the preorder. So we can study the relative non-classicality of assemblages. And what we showed is that assemblage conversion under LOSR can be tested using a single instance of a semi-definite program. So one assemblage is said to be more non-classical than another if it can be fully converted to the latter. So if we have the black assemblage and we can convert it into a different one, the one with primes with free operations, well, it means that they can be used, for example, for the same task because they have, this one will be at least as non-classical as this one. So we showed that checking such conversions can be tested by checking if the following program is feasible. So I have the semi-definite program here, but maybe let me not go into details about it. If any of you is like interested in the details, we can talk about it later during the questions. But the important lesson here is that how this program works is that you just input two assemblages and it tells you whether one can be converted into the other. And it works really fast. It's just a single instance. So it's really amazing because it's a great tool to study the relative non-classicality of assemblages. And we used it to study the structure of the preorder. And one interesting result that we found is an infinite family of incomparable resources. So resources that none of them can be converted into any other. And this family goes like as follows. So what we checked is that we had a scenario where we have Alice and Bob, and they share this state here. So they share a partially entangled state. Now Alice performs sigma z and sigma x measurements on it. So such an assemblage would be described like this. So Alice performs this measurement, Bob does nothing, and they share this partially entangled state. But now something else that we allow is mixing with noise. So the assemblage that we study is defined here. So it's parameterized by these two parameters, theta and p, where theta corresponds to this theta here in the partially entangled state, and p corresponds to the level of mixing with noise. So you can see here that with some probability, we create this element of the assemblage, and then we mix it with noise. And now the results of the program that I just showed you are presented in this graph here. So here, each dot corresponds to one assemblage. So for example, this one is an assemblage created where Alice and Bob share a state with theta being equal to pi over 4. So it's a so-called maximally entangled state. And they don't mix it with noise because p is equal to 1. And now the arrow from here to here means that under LOSR operations, we can convert this assemblage to this one, where this one is when Alice and Bob share a state with theta being equal to pi over 12, and they mix it with noise with this p being equal to 0.9. So as you can see, we can, like using the SDP, we can check whether different conversions are possible. But one interesting property that we can see here is in this family here, so for p being equal 1, for different values of theta, no conversions are possible. We actually we checked it analytically, and we showed that this is a family of incomparable resources. So for all values of theta from 0 to pi over 4, so like up to a so-called maximally entangled state, all of these assemblages for p being equal to 1 are incomparable. And yeah, we also developed some new EPR monotones in order to confirm this result analytically. Okay, as I promised, I'll now compare it to prior work, which was a resource theory of so-called steering under stochastic local operations and one-way classical communication from Bob to Alice. So this set of free operations is, of course, a valid set of free operations for EPR scenarios, which means that it cannot create a resourceful object. And it goes as here. So again, in black, we have the original assemblage, and in green, we have the free operation. So here, Bob has an instrument that he performs on his part of the state. And as an output, he gets, first of all, the classical variable that he sends to Alice, and also his quantum state. And now Alice has a classical pre-processing of her variable that depends on the message that she received from Bob. And she also has a post-processing. So the motivation behind this set of free operations was that the authors claim that it's the most general set of free operations that does not compromise the security of one-sided device-independent quantum key distribution protocols. For them, steering is a useful resource. So the motivation here is a particular protocol in quantum information. Okay, so if you want to compare it to our work, to LOSR approach, the first thing that we can show is a pretty big difference. So the two resource theories actually have different pre-orders, which means that if we have a set of assemblages and we want to study it, and we will study it with two different approaches, this one here and with our LOSR approach, we can actually get different results because the pre-orders are different. Now, our LOSR approach has some conceptual advantages over this one. And one is that it has a clear physical motivation. So motivation for this approach here as one-way LOCC is this one-sided device-independent quantum key distribution protocol, while for our LOSR approach, the conceptual underpinning is more foundational because it comes from the causal structure of the scenario. And because of this, we have this unification of every type of non-classical correlation in Bell-like scenarios. So we have a single LOSR resource theory for common cause scenarios. And there are also some technical advantages. So for example, our LOSR approach is simpler to characterize and study. This SDP, this semi-definite program, is a good example that in our approach, it's really easy to study the conversions. And the other technical advantage is that our approach for the bipartite scenario actually has some direct generalizations, for example, to multipartite EPR scenarios, but also to Bob with input and channel EPR scenarios, where by channel EPR scenarios, I mean something that's usually referred to as channel steering. And we left Bob with input at channel for future work, but we did study the multipartite scenarios. So let me just say a few words about this right now. So let's go to a multipartite setup, which means that we now have more Alices. For example, in this picture here, we have two Alices. And as you can see, everything just generalizes from the bipartite case. So we still have a common cause. So we have the shared randomness that goes to each party. And each party also can perform local operations. So we have local operations for Alice 1, Alice 2, and for Bob. And what we showed in the multipartite scenario is that assemblage conversion can be tested using a single instance of a semi-definite program. So we generalize the program that I showed you before to work for multipartite scenarios. And we also found a family of incomparable resources. So we have these two results that are very, like they go in analogy to the bipartite case. But one thing that's a little bit extra here is a clear definition of a multipartite free assemblage. So again, free assemblage is one that can be created using only free operations. And since we study non-classicality, the free assemblage will be a classical assemblage, or how people usually call it in the literature, so an unsteerable assemblage. And actually, there are a lot of definitions of a free multipartite assemblage in the literature. The most general that you will find is this one. So it's that an assemblage is free if it can be decomposed like this. So we have this probability distribution for Alice's, and we have the state for Bob. And actually, in the most general definition, there are no constraints on this probability distribution here. So for example, this probability distribution is allowed to be signaling for each lambda as long as the signaling averages out when we sum over all lambdas. So such a thing is usually referred to as fine tuning, that we have this kind of undesired effect for each lambda, but then it averages out. And it can be seen as problematic from some perspectives. And there are a few different problems that arise for this definition. Maybe I will not really go into detail here, but we don't have any of these problems in our LOSR approach. So if we look at the set of free operations again in our LOSR approach, well, it's pretty clear that A1 prime depends only on X1 prime and lambda, and A2 prime depends only on X2 prime and lambda. So this probability distribution in our case will factorize. So in our LOSR approach, a free assemblage is one that decomposes like this. So we don't really have any problems with signaling or any of the ones that appear for this more general definition. Okay, so that's pretty much it. Let me just make some final remarks. So what I just presented to you was a resource theory of common-cause assemblages for bipartite and multipartite EPR scenarios. And it was motivated by a clear causal interpretation of an EPR scenario that is a common cause that Alice and Bob share. Thanks to this causal interpretation, this notion is a unified notion of common cause resources, and it works, for example, for EPR scenarios, but also for Bell scenarios and entanglement. We showed that testing convergence is numerically tractable, which is very useful if you want to study the pre-order of resources. And we use this result to show some interesting properties of the pre-order. And finally, in the multipartite case, we had a well-motivated definition of a free multipartite assemblage. So thank you for your attention, and I would be very glad to take any questions.
Okay, thank you, Beata, for your talk. Now we have some minutes for questions or comments. If somebody make a question, please indicate it in the chat. If not, yes.
Yes. Okay, thank you. Thank you for the talk. I think it was very well presented. I am a little confused about the general picture of what you're doing. Okay, let me try to state what I think is your project, and let me relate it to some issues that seem to be relevant. Okay? So if I understand you correctly, you first presented the view of Schrödinger, according to which there seems to be some type of action at a distance in a typical EPR scenario. And you said correctly that EPR themselves, and in particular Einstein, had this view that, well, it might be that in reality, quantum mechanics is not complete, and that the quantum state somehow reveals, is about the knowledge of Alice or Bob. Okay, that perhaps there is something more to the quantum state. And in your case, there seems to be a reference to a common cause in the past of Alice's and Bob's labs. Okay, and you seem to think that you can recover locality by this way of thinking. And the problem I see is that, well, that is precisely the starting point with Bell's work and with his theorem. And his question was, well, can we recover locality by doing something like whatever Einstein thought? And his theorem is, no, you cannot do it. You cannot have a local theory. And here's why: because any theory that is non-local in this sense is going to make these inequalities. It's going to satisfy these inequalities. We go, we check, time and again, we notice that the inequalities are violated, and the consequence seems to be that, well, any non-local theory is not going to work. So let me know, what am I missing, and how is
Well,
your...
you're not. Yeah, so you're not really missing anything. So let me start with your Bell comparison. So this is a Bell type experiment, right? We have a common cause and we have two parties and they make measurements. So now if this common cause is classical, just by studying this causal structure, so the fact that you have a common cause and you have inputs and outputs, you can derive Bell inequalities. And now if the common cause is classical, you can just like the upper bound on the CHSH inequality is 2. If the common cause is quantum, it's 2 times the square root of 2. And if it is allowed to be anything more, but there is still non-signaling between the parties, we have the PR box, right? So it goes up to 4. Now, it's the same with EPR scenarios. So if this is a classical common cause, then the assemblage is free and it's classical. So as you said, it kind of recovers locality in this sense. But if it's quantum, we get assemblages that cannot be explained just with classical physics.
Okay, but then you must somehow be violating one of the assumptions of Bell's theorem, right? You must be violating settings independence, either by postulating some sort of common cause between the state of lambda, the common cause, and the settings of Alice and Bob, or you're assuming something like a retrocausal theory in which Alice's settings somehow influence the state of the system, the common cause.
Well,
or am I missing something?
So for example, here you can like put a box and you can make Bob make the measurement. And then it will be just like a standard Bell scenario, right? So one way of looking at an assemblage would be to see whether if Bob makes a measurement, we violate a Bell inequality. And like you could do so if the shared state is entangled, right? But if it's classical, then you cannot. So you have to draw this line between what's classical and what's non-classical. And both for Bell scenarios and for EPR scenarios, this line can be decided based on the nature of the common cause. So if a common cause is classical, then you will not violate a Bell inequality. But if it's quantum, so if they share an entangled state, then you will get some quantumness in this scenario.
Thank you.
Does it answer your question, or I'm not quite sure?
Perhaps we should let other people make questions, and perhaps another time we can continue.
Okay.
Thank you.
There is another question from Federico Pollitt, but we have Federico.
Yes, thanks, Beata, for this very nice talk. I wanted to ask you whether there is a simple explanation of why you have a pre-order and not a partial order or even a lattice, as it happens in other resource theories.
Not really. So one thing is, where do I have it? So the structure of the preorder here is very much inherent to the structure of the preorder for LOSR entanglement. So for example, in LOCC entanglement, what you have is that the conversions between states with an as the value of theta gets smaller, you can actually convert the states into a different partially entangled states. In the LOSR entanglement, it's not the case. So it's already in the LOSR entanglement that you have family of incomparable resources. So for the case of assemblages, this case is it just translates from the states to assemblages.
Okay, thanks.
Okay. There is another question or no? If not, we thank to Beata again for the talk and the people who participated.